If we want to send human beings to Mars, the current travel time sits at roughly 9 months. But picture a spacecraft capable of making that exact same trip in just 3 months. Expand that radius outward, and you're looking at human missions to the moons of Jupiter, Saturn, Uranus, and Neptune, crossing distances that are entirely out of reach for any vehicle we fly today. Our current reality is much slower. With the technology sitting on our launch pads right now, humanity is effectively forced to crawl through the solar system. The math keeping us tethered was worked out in the early 20th century by Konstantin Tsiolkovsky. The Tsiolkovsky rocket equation dictates a hard physical limit on exactly how much energy you can squeeze out of traditional rocket fuel. This chart shows the primary measure of a rocket's fuel efficiency, a metric known as specific impulse. Standard chemical engines, the kind that burn a mixture of fuel and oxidizer, hit a strict thermodynamic ceiling. They usually max out at a specific impulse of about 250 to 450 seconds. That low ceiling traps us in a vicious cycle. If you want to travel further into deep space, you have to pack massive reserves of fuel. That fuel is heavy. To lift that extra weight, you have to pack even more fuel just to get off the ground. Escaping that mathematical loop is the only way we will ever build a true deep space infrastructure. And scientists already designed, built, and successfully tested the engine to do it over 50 years ago. In 1955, the United States Atomic Energy Commission and the Air Force launched Project Rover. Deep in the Nevada desert, they began testing a totally different kind of propulsion. Looking at this cross-section of a nuclear thermal rocket, you can see how it bypasses chemical combustion entirely. Instead of burning a fuel and an oxidizer, the engine houses a highly compact nuclear fission reactor. Liquid hydrogen is pumped directly into this reactor core. The intense radiation flash heats the hydrogen to nearly 3,000 degrees Kelvin. The gas expands violently and blasts out through the nozzle to create thrust. Because hydrogen is the lightest element on the periodic table, it exits the nozzle at staggering velocities. That pushes the specific impulse up to roughly 850 seconds, nearly double the absolute maximum limit of our best chemical rockets. This left the drawing board. By the late 1960s, a spin-off program called NERVA was physically building these engines. The prototypes were wildly successful, with some firing at full power on test stands for over an hour continuously. Then, in 1973, the US government canceled the entire program. The Apollo missions had ended, aerospace budgets were shrinking rapidly, and growing environmental concerns regarding nuclear safety made the project politically toxic. The engineering sat dormant for decades. Finally, in 2020, DARPA and NASA launched a $500 million joint initiative called Project DRACO, aiming to actually put a modern nuclear thermal engine into orbit by 2027. The math for human exploration was highly compelling. Reducing a Mars transit time from 9 months to 3 or 4 months severely limits an astronaut's exposure to zero gravity and deep space radiation. But history repeated itself. In early 2025, DRACO was abruptly canceled, and all funding was slashed. This time, safety fears didn't kill the engine. The private sector did. Plunging launch costs from reusable rockets, pioneered heavily by SpaceX, meant that the massive government spending required to develop a nuclear engine simply couldn't be justified against cheap, readily available chemical alternatives. DRACO's cancellation doesn't mean nuclear spaceflight is dead. The aerospace industry is heavily pivoting toward programs like the US Air Force's Jetson program and Russia's Zeus module. These focus on nuclear electric propulsion. This flowchart illustrates a totally different approach. Instead of using the reactor to directly heat a gas, the fission process generates raw electricity. That electricity is then used to power highly efficient ion or plasma thrusters. You lose the aggressive, high-powered thrust of a thermal engine, but in exchange, the specific impulse skyrockets into the thousands of seconds, making it the most mathematically efficient way to push a payload across the solar system. There's an operational bonus too. When a ship reaches its destination, say a permanent lunar base, that same reactor can be repurposed to generate continuous surface power, keeping habitats alive through the freezing month-long lunar night when solar panels are useless. Any discussion about putting a nuclear reactor on top of a controlled explosion raises the obvious question of launch safety. If the rocket explodes on the pad, you have a massive radioactive disaster. Engineers solve this with the cold launch protocol. During liftoff, the reactor is entirely inert, It contains no highly active fission products and is physically incapable of causing a meltdown until the spacecraft reaches an orbit of at least 700 kilometers, where the chain reaction is finally initiated. We can theorize about engines that utilize nuclear fusion, or even antimatter drives capable of converting 100% of their mass into energy. There are active proposals like the Breakthrough Starshot initiative, which aims to bypass onboard engines entirely, using ground-based lasers to accelerate tiny solar sails up to 20% the speed of light. But producing a single gram of antimatter currently costs tens of trillions of dollars, and fusion remains elusive. Those concepts require physical breakthroughs we haven't achieved. Nuclear fission is an engineering problem we solved half a century ago. Chemical engines are highly effective tools for escaping Earth's gravity well. But the sheer math proves they cannot carry us across the massive distances of the outer solar system in any reasonable time frame. Expanding our footprint across the planets doesn't require us to wait for a miraculous scientific discovery. We just have to decide to use the engines we already built.